Let's take some time and talk about 6.6. And the title of this section is the Fundamental Theorem of Algebra. So basically we're getting at what the heart or what the most basic idea in algebra is. In order to talk about this, we're going to cover some things called the irrational root theorem and the complex conjugate root theorem. And I want you to become thinking about how you would compare and contrast these two theorems. So for example, if you had to draw a Venn diagram, what would go on the rational root side, what would go on complex, and then what exactly do they have the same? Because there's definitely some similarities here too. And that's what I want you to be thinking about, because the more we can identify what's the same and what's different, the more we'll understand them, right? And the better we'll be able to use them. First of all, a lot of the same ideas have been coming up, but in totally different ways. And so I want to take you through a quick review of some things you've heard this chapter. All of these actually imply the same thing. So the first one is, a real number r is a root of the polynomial equation p of x equals 0. We've talked about how to find roots, right? And roots are solutions. They're numbers that make the function equal 0. That's the same thing, or that means the same thing as saying that if you evaluate the function r, the polynomial at r, it will equal 0, right? If you plug in r, the answer is 0. Okay? That's the same as saying r is an x-intercept of the graph, right? If we graph it, that's where it crosses the axis. We've talked about that. We've graphed it and found solutions that way. And that means that x minus r is a factor of p of x, right? If we were to factor the polynomial, one of our factors would be x minus r, where r is a root, r is an x-intercept. When you divide the rule, okay, now the rule, that sounds funny, but what we're saying is when you divide p of x, the polynomial, by x minus r, the remainder is 0, right? We'd use synthetic division, and we'd put r, that root, that x-intercept, we would use that up in the corner. Okay, and the remainder would be 0, because when you evaluate the function, it gives 0. Because it's a root, it would be 0. All of these are very connected. The last one being r is 0 of p of x. 0, root, x-intercept, having to be a factor. These are all connected, which is super cool, because when we say one thing, it can lead us to something else. When we say we have a root, it can lead us to getting a factor. When we say we have a factor, we know an answer, right? If we have a 0, if it says find the zeros, we're finding the roots. These are all connected, and so we need to be able to understand that, hey, if I tell you that 6 is a root, that means that x minus 6 is a factor. And when I divide the polynomial by x minus 6, my remainder is 0. If I plug in 6 to the polynomial, it equals 0. All of these are connected, which is super cool. Like, how sweet is this, for real? Okay? All of this and all of these connections lead us into this fundamental theorem idea. Okay? The fundamental theorem of algebra says every polynomial of degree n greater than or equal to 1, right? We wouldn't want to talk about a degree 0 polynomial. So we're talking about 1 or larger, linear, and so on. Has at least one 0, where 0 may be complex. That's why we need to be able to talk about complex, because they're just as important, right? They're funky, we don't always like them, but they are important. Okay? Here's really what I like to think of the fundamental theorem of algebra. This is great, but this is dumb. It's kind of weak. This is the moneymaker. I love this. Every polynomial function of degree n greater than or equal to 1 has exactly n zeros. Notice the n's are the same, including multiplicities, right? We have to account for sometimes a 0 occurs more than one time. But this is what this means. Quadratic, 2 solutions. Cubic, 3 solutions. Degree 4, 4 solutions. Degree 5, 5 solutions. Degree 100, you'd have to solve and find 100 solutions. Like, how sweet is that? I love it. Okay, I know maybe you don't love it, but I think it's pretty darn sweet. And so when we find all the zeros, we know exactly how many we're supposed to have. And that helps us to make sure we don't miss any, and it also helps us to work backwards. And the working backwards, starting with the zeros and writing a polynomial, is what we're going to work on. Okay? In order to do that, we just have to have a quick talk real quick. We can use the fundamental theorem of algebra to completely solve a polynomial function. And there's 3 strategies rely on. One of them you've seen before, pretty in depth, the rational root theorem. Some of you hated this, but it was still pretty cool. The rational root theorem lets us generate a list of all possible roots, right? We use p and q. P is any factor of the constant term. List them all, plus or minus 1, plus or minus 2, plus or minus 11, plus or minus 22, for example. Every factor you can think of. Q is all the factors of the leading coefficient. Our favorite one is when leading coefficient's 1, because then we only have a 1 right here. Now, that doesn't always happen, and sometimes we have to list all the factors. What this means is sometimes we have that huge list, and that's when we go to the graph, and that's when we work from the graph to see, hey, which ones do we actually care about? Right, we've done that. There's two other ones that I want to tell you a little bit more about. The first is the irrational root theorem, right? Irrational meaning taking the square root of a number that's not a perfect square. The irrational roots occur in pairs, and they occur in pairs of a plus and a minus. Completing the square was all about plus or minus. Quadratic formula, plus or minus the square. Yeah, that plus or minus is how those pairs come. Okay, so what we have here is a plus the square root of b, then a minus the square root of b is also a root. And that goes for, let's say a wasn't here. I'll use the power of pointers to cover it up. If the square root of b is a root, then the negative square root of b is a root, right? Okay, so we need to identify that those do occur in pairs. Then the same thing happens for the complex conjugate roots, right? If you have a complex root, you'll also have the conjugate, and they occur in pairs as well. So irrational roots occur in pairs, complex roots occur in pairs. That's something they have the same. Okay, here it's a plus bi, and here it's a minus bi. Okay, so a plus bi, a minus bi. So whenever you see one root, you can easily identify another. Okay? If you see 6i, you know, hey, guess what? Minus 6i also has to be a root. If you see 3 plus the square root of 2, hey, guess what? 3 minus the square root of 2 is also a root. It's kind of cool. Okay, anyway. Let's look at an example problem, because I want to show you how this works. Write the simplest polynomial function with these three zeros. 1 plus I, the square root of 2, and negative 3. Okay? We can write a polynomial function that has these zeros. The first thing we have to do, though, is we have to determine what all of the zeros are. And what that has to trigger in your brain is, hey, if I see an irrational zero, I need to have its partner. If I see a complex zero, I need to have its conjugate. Okay? They must occur in pairs. If 1 plus I is a zero, then so is 1 minus I. If the square root of 2 is 0, then so is the negative square root of 2. So really, we have 5 zeros here. 2 complex, 1 plus I, 1 minus I. 2 irrational, square root of 2, negative square root of 2. And 1 real, that negative 3. So the polynomial must be degree 5, x to the 5th. And all 5 zeros will help us write the function in factored form. Okay? When I say factored form, think back to what I said at the beginning. If this is a 0, then x minus this number is a factor. So, oofda. X minus my first 0, 1 plus I. X minus my second 0, 1 minus I. There's my pair. X minus the square root of 2, x minus the negative square root of 2. Those are my irrational pair. And then x minus negative 3. That one's just chilling in the back. Doesn't have a partner. Okay, real or rational, I should say. Rational roots don't have partners. It's only irrational and complex because it comes from, once again, plus or minus. Okay, so I've written it all the way out, and this one's probably a little out of control, but it's okay. It's good for us to look at. Multiply the complex pairs and irrational pairs together first. So I want to live in just these first two, and I want to multiply those two together. And then I want to live here, and I want to multiply these two together. And of course, I know that minus a negative turns to a positive. If you do it right, there should be no squares anymore. There should be no i's left. So everything should be whole number, beautiful coefficients. Love it. Okay. So the first step is in this box. The first step is, hey, this x squared minus 2x plus 2, that comes from the 1 plus I stuff. This x squared minus 2, that comes from the square root of 2 stuff. This x plus 3, we'll touch it later. Then I'm going to work with just these two. I'm going to get x to the 4th minus 2x to the 3rd plus 4x minus 4. Okay? That's just from multiplying these two together. There's a reason we had to practice multiplying so in depth, right? I gave you some ugly problems, but that's because I wanted you to get good at this, because this is serious business now. Then we can finally touch the x plus 3 at the very end, and we get x to the 5th. Love it. We said it had to be degree 5. X to the 5th plus x to the 4th minus 6x to the 3rd plus 4x squared plus 8x minus 12. Okay? If you don't totally believe me, start with this. Start with this and multiply and see if you can take it all the way through. My first thing here would be, if I was multiplying these, which I was, take and make this -1 and -I, and -1 and +I, right? And then if you're a lattice person, this is going to be a 3x3 lattice, okay? Here, do the same thing if you're a lattice person, although foil might work better for this one. I would say lattice here, or just great old distributive property on steroids, it's up to you. And then foil, and then just leave this chilling at the end. Right here, you could do lattice, or you could do distributive property, and then get to here. Now, and then here, either distributive property or lattice. It's up to you. I'm giving you choices here. Whatever works best for you. Okay? I'd be happy to show you how to do this before school tomorrow. If you come in and said, Ms. Vistar, I'm so confused, yeah, come see me. I'd be happy to walk through this multiplication with you, just to make sure we've got it. In the meantime, though, guess what? I want you to try one. This one's on your worksheet. Oh, my bad. So give it a shot right now. Just give it a shot. Come with it done. We'll talk about it. We'll do it together. If you've got it, great. You can just get rolling. But if you don't got it, at least you'll have tried and can kind of meet me halfway. Right? The simplest polynomial function was 0, 6i. Psst, guess what? That means minus 6i also shows up. So 6i, square root of 5. Guess what? Negative square root of 5 as well. Remember those pairs. And then -4. So 6i, square root of 5, -4. My hint to you is this will be degree 5. You try it. I'm asking you to play ball a little bit. You give it a try, even if you just set up the 5 factors. Even if that's all you can get done. Awesome. I love it. Okay? Try multiplying a little bit. Give it a little bit of a shot, okay? And we'll keep practicing, and I know you're going to get this. Okay? I know you'll get it. So you make it happen. Come with it done. Come with it attempted. Come at least having looked at it. That's all I'm asking. Okay? The fundamental theorem of algebra is pretty darn sweet. Okay? There's lots we can do with it, right? We can solve, we can rewrite. It's pretty sweet. Okay? And my favorite part is it's the fundamental. It's the most basic at the heart of algebra. And all algebra is solving equations, right? Solving equations, solving equations, solving equations. Some of you are going to kill me because you're so sick of solving equations. But we solve them so much because that's the fundamental theorem. If you have this degree, you have this many solutions. So of course we're going to solve because we got to find all the solutions. Okay? And so now we're working with the solutions to rewrite. And so we're kind of going backwards with it, but it's still at that same idea, that same core idea of the fundamental theorem. Okay? For tomorrow, 6i, square root of 5, -4. Give it a shot. Do your best. Remember, if you want to know more about this one, I'd be happy to help you with this one before school. Otherwise, make this one happen. You can do it. Give it a shot. Give it a shot. Let's go, people.